Welcome everyone to our today's talk on FastZIP, faster and more secure zero interaction pairing. My name is Mikhail Fomichev, and this is a joint work with Julia Hesse, Lars Hellman, Tim Lippert, Jun Han, and Matthias Hollig. We're witnessing a constant increase in smart devices, such as appliances, wearables, or connected cars, and their numbers are rapidly growing. Soon, there will be billions of various smart devices, which will become an essential part of our everyday life. Pairing is the process of establishing a shared secret key between previously unknown devices without any trusted third party. A Bluetooth pairing is a famous example here. Using this shared secret key, devices can perform encryption and authentication, protecting the data they exchange. However, user-assisted pairing schemes, such as entering a password, cannot be easily applied in the Internet of Things because of two reasons. First, the rapid increase of smart devices requires a prohibitive user effort to pair these numerous devices, which simply does not scale. Second, many smart devices lack user interfaces, making user-assisted pairing infeasible in the first place. In zero-interaction pairing, two devices pair without user involvement, utilizing their ambient context such as audio captured by their onboard sensors, for example microphones. Specifically, the captured context is first translated to a sequence of bits called fingerprints, which are then input to a key agreement protocol to establish a shared secret key. Hence, zero interaction pairing promises high usability and can work on many devices. The state-of-the-art zero interaction pairing schemes, we refer to them as ZIP schemes, have three major limitations. First, prolonged pairing time, requiring minutes and hours of context measurements to establish a shared secret key. This happens because the schemes rely on a cryptographic primitive called fuzzy commitments, where the entropy of a shared secret key is equal to the entropy of fingerprint bits input to the key agreement protocol. Since contexts often change slowly, obtaining enough high entropy bits to secure the shared secret key takes a prolonged time. Second, the use of fuzzy commitments requires the fingerprints derived from context to have sufficient length, for example 128 bits, and have high entropy. Otherwise, the shared secret key can be brute forced by an adversary who repeatedly guesses the used fingerprints. Recent works find that many state-of-the-art ZIP schemes produce fingerprints with limited entropy, which is not accounted for. Hence, these schemes are exposed to offline attacks. Third, many ZIP schemes are vulnerable to predictable context attacks, such as a replay attack, because they rely on a single sensor modality, for example acceleration, to capture context. This allows adversary to effectively replicate the context. In this work, we ask ourselves the following question. How can we reduce the pairing time while providing resistance to brute force offline attacks and predictable context attacks? To answer this question, we propose a novel zip scheme called FastZIP. FastZIP is built upon two design decisions. First, a better cryptographic primitive than fuzzy commitments called FPAKE, which allows establishing a strong secret key from short fingerprints while being robust to offline attacks. By relying on short fingerprints, FastZIP can significantly reduce the pairing time. We show how to adapt FPAKE for practical zero interaction pairing and provide the first implementation of this protocol. Second, we utilize sensor fusion, where we combine fingerprints derived from multiple sensors to eliminate predictable context attacks. Sensor fusion further assists FPAKE in shortening the pairing time, as we obtain more bits from context, accumulating entropy faster. FastZIP works as follows. First, two devices capture their context using multiple sensors. Second, sensor readings that do not capture sufficient ambient activity, namely they have low entropy, are discarded. Third, fingerprint bits are derived or quantized from sensor reading containing sufficient entropy. Fourth, fingerprints from different sensors are fused, namely concatenated, into a single fingerprint. And fifth, these fused fingerprints produced by each device are input to the FPIC protocol, which outputs a shared secret key if the two fingerprints have sufficient similarity. To enable sensor fusion, we address an interesting challenge of devising a fingerprinting approach that applies across various sensor modalities, produces fingerprints without entropy biases, and is efficient to implement. We not only implement FastZIP and evaluate it on real-world context data that we collect, but also publicly release this data along with the source code of our scheme and the FPIC implementation. To show the feasibility of FastZIP, we implement and evaluate it for a novel use case of pairing smart devices inside a moving car. For this, we equip 4 different cars with multiple sensors each and collect accelerometer, gyroscope, and barometer data from over 800 kilometers of driving. We cover various settings such as urban, rural, and highways. Despite being evaluated for intra-car device pairing, the design of FastZIP generalizes to other use cases, for example, smart home or wearables. To collect sensor data, we use smartphones distributed inside a car, such as on a dashboard, passenger seats, and inside a trunk. FastZip allows reliably pairing devices inside the same car while resisting various attacks. We show that sensor fusion increases successful pairing rates for legitimate devices while decreasing them for adversarial devices. Also, FastZip pairs up to 3 times faster than any state-of-the-art zip scheme, and it runs efficiently on off-the-shelf devices. We see that true acceptance rate, showing the rate of legitimate pairings, is relatively high, ranging between 84 and 91% for individual sensors. We also observe that TR increases with the intensity of ambient activity, for example, road bumpiness on a highway, and that individual sensors have potential to complement each other. However, attacks on individual sensors are also feasible. We see that in the injection attack, where the adversary uses self-chosen sensor readings to pair with legitimate devices, the false acceptance rate is just below 4% for 3 out of 4 sensor modalities. Even worse, replaying sensor data collected on the same route where a car with legitimate devices drove shows FAR of up to 20% for low-varying sensor modalities such as barometer, capturing altitude changes along the route. By fusing more sensors, we see that true acceptance rate steadily increases, exceeding 90% in most cases. Importantly, the sensor fusion allows preventing the above injection and replay attacks, showing error rates close to 0 by combining more than 2 sensors. In addition, sensor fusion is indispensable in preventing advanced attacks such as similar context attack, where the adversary closely follows a victim car with legitimate devices. We see that none of the individual sensors alone can prevent this attack. However, combining 3 and more sensors decreases false acceptance rates to almost 0. We demonstrate that even without the help of sensor fusion, FastZIP based on the FBake protocol shows 2 to 3 times faster pairing time compared to state-of-the-art zip schemes that utilize fuzzy commitments in the same setting. This graph depicts the pairing time obtained from our collected sensor data, which corresponds to theoretical calculations of pairing time that we also conduct in the paper. Finally, to show the practicality of FastZip, we benchmark our FBake implementation on the Raspberry Pi using fingerprints derived from our data. We see that establishing a shared secret key using a fingerprint fused from 4 sensor modalities takes around 8 seconds on average. This time is dominated by communication overhead when devices exchange messages over a wireless channel, Wi-Fi in this case. Given that our prototype implementation is Python-based without any performance optimization techniques applied, we're positive that FastZip is deployable on commodity IoT devices. We outlined 3 interesting discussion points for FastZip. First, we demonstrate how the building block of FastZip can be adapted to other use cases such as wearables. However, it would be interesting to see the real-world performance of FastZip in one of these cases, or utilizing a completely different set of sensors to capture context. Second, we envision FastZip to work on a continuous stream of sensor data, eliminating the need for tight time synchronization between devices. However, an open question is how to handle desynchronization events, for example, clock drift that may occur in real time. Third, the current version of FastZip for intra-car device pairing assumes devices to be fixed inside the car. However, user interaction would introduce extra noise to sensor readings, which needs to be identified and eliminated. In conclusion, we have demonstrated that FastZip built upon a better cryptographic primitive called FBake, combined with sensor fusion, reduces the pairing time by up to 3 times compared to state-of-the-art zip schemes, and that FastZip provides resistance to brute force offline attacks and predictable context attacks. By making the implementation and data on which FastZip was validated available, we enable other researchers and practitioners to build better zero-interaction pairing schemes for various use cases. I thank you for your attention. Our paper will be available on the ACM library, and its preprint can be already found on arXiv. Our source code and data are also available on GitHub. I will be happy to take questions in the conference chat now, and of course, you are welcome to contact me via email. Thank you.